Hello students, welcome to EPG Pathshala. I am Dr. Ajit Kumar Mahapatra from the Department of Physics and Astrophysics, University of Delhi in India. Today we are going to discuss about a module on surface morphology using scanning electron microscopy. This comes under the paper titled Characterization of Materials 2. From this module, we may get to know about the following things: the surface morphology and topography of the materials, the secondary and backscattered electrons, how it produces in the material, and third, about the electron beam interactions. The surface morphology and topography. Here, the morphology is a qualitative evaluation of the three-dimensional shape of a surface, and topography provides the quantitative dimensions to the feature. The morphology studies the shape, texture, and the distribution of materials at a surface and is best evaluated using imaging techniques such as optical microscopy or electron microscopy. These methods can also provide layer thickness using optical profilometer or taking image of transverse section of the specimen. However, determination of roughness, step heights, and feature size can be addressed using atomic force microscope, stylus profilometry, or optical profilometry. Few analytical imaging techniques are also used, generally high resolution optical microscopy, scanning electron microscope, field emission scanning electron microscope, the ultra high resolution scanning electron microscope, focused ion beam scanning electron microscope, and scanning transmission electron microscope and transmission electron microscope. So, the electron microscope is how it works. The waves in electron beam can be coherent, that is, the waves of same wavelength, or incoherent with waves of different wavelengths. The electron source in the microscope generates a beam of coherent electron waves, which when fall on the surface of the specimen, it interacts with the atom of the specimen and can form beams consisting of either coherent or incoherent scattered electrons. The electron beam generated from the thermionic electron gun passes through the electromagnetic lenses and directed towards the column of the microscope and falls onto the sample surface. Any changes in the electromagnetic wave after interacting with the sample surface could affect the movement of the electrons. The positive charge of the atom is strongly concentrated at the nucleus, whereas the negatively charged electron atoms are much more dispersed in the cell structure. Electron entering into a material interacts as a negatively charged particle with the electric field near the nucleus of the atoms in the specimen. These interactions can be classified into elastic or inelastic interactions and are discussed briefly in the following sections. Optical and electron microscopes. The schematic diagram with details of components for the optical and electron microscopies are shown in the below figure. The wavelength of visible light used as sources are generally between 400 to 700 nanometer for optical microscopes, whereas the wavelength of the electrons used for the sources are approximately 0.02 nanometer in case of electron microscopes. Generally, the objects with dimensions less than half the wavelength of the microscope's illumination source cannot be visible under the microscope. The optical microscopes use visible light which has a minimum wavelength of 400 nanometer and cannot image the objects smaller than 200 nanometer. The wavelength of electron is thousands of times shorter than the visible light, enabling the electron microscopes to be able to resolve this issue and provide better magnification to image the objects at very low dimensions. Hence, the electron microscopes can be used to visualize the inorganic, metallic, organic and biomolecular entities at atomic scale resolution. Electron microscopy is a technique that offers unique possibilities to capture images at nanometer resolution for understanding the structure, topology, morphology and composition of a material. Primary electrons after collision with atoms with the specimen impart energy to the specimen, thereby resulting a loss of energy or change in momentum of the primary beam electrons that gives rise to a production of equivalent amount of energy in other form. These various forms of energy phenomena produced during the electron specimen interaction have the potential to provide important information about the nature of the specimen. When an electron hits onto a material, different interactions can occur as summarized in the figure below. The electron specimen interactions can provide the information about the specimen composition, the topography, crystallography, electrical potential and local magnetic fields. As an electron travels through the specimen, interaction volume, its scatterers lose energy and changes the direction with each atomic interaction. Scattering events can be divided into two general cases. First is elastic scattering and second one is inelastic scattering. The elastic scattering. The electron beam approaches toward the specimen and electrons with various energies interact with the localized atoms. During this process, electron trajectory changes and scatters. The process in which the kinetic energy and velocity remain essentially constant, that process is known as elastic scattering or electron backscattering. No energy transfer takes place from the electron to the sample and as a result the electron is leaving the sample exhibiting its original energy E0, that means E is equal to E0. A strong elastic scatter very near to the nucleus may result in beam electron leaving the specimen via backscattering called backscattered electrons or BSE. These electrons provide an important information for SEM imaging. The probability of elastic scattering increases strongly and varies as square of the atomic number Z square. Also, since the heavier atoms have much stronger positive charge at the nucleus, the probability of the elastic scattering decreases and generally depends as a square of the electron energy, which is 1 by E square dependence. If the electron passes through the sample without any interaction, no energy is transferred. Such electron beam is consisting of electrons that pass through the sample in the direction of the incident beam without any deviation. Inelastic scattering. The inelastic scattering is a process in which energy is transferred from the incident electrons to the sample, and henceforth the energy of the electron after interaction with the sample is consequently reduced. That means E0 is greater than EL. In elastic scattering, the trajectory of the incident electron is only slightly perturbed, but energy is lost through interactions with the orbital electrons of the atoms in the specimen. The inelastic interactions produce diverse effects, including the secondary electrons, phonon excitations, cathodoluminescence, continuum radiation, characteristic X-ray radiation, plasmon production, and Auger electron production. The signals caused by inelastic electron-matter interactions are predominantly used in the methods of analytical electron microscopy. Secondary electrons. Several mechanisms of inelastic electron matter can lead to the ejection of secondary electrons, abbreviated as SE. The first kind is electrons located in the valence or conduction band, which are loosely bound outer electrons, need only the transfer of a small amount of energy to overcome the work function and to be ejected into the vacuum. Typically, they carry energies below 50 electron volt and are thus designated as slow SEs. These secondary electrons are utilized in scanning electron microscope for morphology and surface topography studies. The electrons that are located in the inner shell are strongly bound and less readily ejected. This process leads to an ionization of the atom and subsequently to the generation of characteristic X-rays or Auger electrons and another kind of secondary electron. These electrons from inner shells can carry large energy and thus they are rather fast, so called as a fast secondary electrons. Topographic information is obtained only from the secondary electrons generated close to the surface and escape. Number of secondary electrons are greater than the number of incoming electrons. They are used to reveal the surface structure of a material with a resolution of about 10 nanometer or better. The secondary electron coefficient is defined as delta is equal to NSC divided by NB. That means the ratio of the number of secondary electrons in specimen divided by number of beam electrons incident on the specimen. The escape depth of the secondary electron is small, a few nanometers, so all of the secondary electron created by the beam electrons at greater depths are lost. For secondary electrons, the intensity is not sensitive to atomic number. It decreases as beam energy increases and increases with the tilt and decreases with the angle of the tilt. The secondary electrons are generated by three different mechanisms. The SE1 are produced by interactions of electrons from the incident beam with specimen atoms. These SEs are produced in close proximity to the incident beam and represent a high lateral resolution signal. The secondary electron, the second type, are produced by interaction of high energy backscattered electrons with specimen atoms. Both lateral and depth distribution characteristics of backscattered electrons are found in the secondary electrons of type 2 signal, and thus it is a comparatively low resolution signal. In the third type of secondary electrons, these are produced by high energy backscattered electrons which strikes the pole pieces and other solids within the specimen chamber. The factors affecting the secondary electron emission. First one, which is affecting the AC electron emission, is work function of the surface. The second one that affects is the beam energy and beam current. The secondary electron coefficient increases as the beam energy lowered. The escape depth of the secondary electron is small, that is in a few nanometers. So, all of the secondary electrons created by the beam electrons at greater depths are lost. The electron yield goes through a maximum at low accelerating voltage, then decreases with increasing accelerating voltage. The third depending factor is the atomic number. More secondary electrons of type 2 are created with increasing the G values. The atomic number dependence is more pronounced at lower beam energies. The fourth factor that is affecting is the effect of surface tilt for secondary electrons. In areas where the surface is tilted relative to the incident beam, the electrons travel greater distances in the region close to the surface of the specimen. This indicates that as the angle, that means the specimen tilt, increases, the secondary electron coefficient increases. The secondary electron can escape from both the sides of ridges and edges. These effects cause tilted surfaces to appear brighter than flat surfaces. Now, the backscattered electrons. Elastic scattering of the electron beam produce backscattered and transmitted electrons as the strong electrical field of the specimen's atomic nuclei deflects them, and no additional electrons are produced for the sample. Where transmitted electrons completely passes through the material, after interacting with it, backscattered electrons are ejected from the top surface of the specimen at high angles. The transmitted and backscattered electrons can have energies from about 50 electron volt up to the accelerating voltage E0. The number of backscattered electron produced from a material may be quantified by its scattering coefficient eta b, which is equal to the number of secondary electrons specimen divided by the number of beam electrons incident on the specimen. This coefficient depends strongly on a sample's average atomic number. Neglecting the effects of E0, the above equation, which is eta b is equal to n VAC divided by NB, yields a good approximation for the coefficient eta b. The B is the backscattered electron respond to composition, allowing the atomic number or compositional contrast. There are few factors that is affecting to the backscattered electron emission. The first one is the atomic number. The backscattered electron coefficient increases with increasing the atomic number. The second factor is the beam energy. The backscattered electron coefficient does not depend strongly on the beam energy. The third one is the tilt. The backscattered electron coefficient increases with tilt as the electrons can escape the surface with less total angular deviation, that is at very high angles that corresponds to the grazing incidence, then the value of NB tends towards unity. And the fourth type is the backscattered electron on angular distribution. The backscattered electron tilt is also affecting the BSE emission. Here, the backscattered electron coefficient increases with tilt as the electron can escape the surface with less total angular deviation. At very high angles, this corresponds to grazing incidence. The value of NB tends to unity. When the surface is normal to the incident beam, the backscattered electrons are distributed symmetrically around the incident beam in a manner described approximately by the cosine function, which is n psi is equal to nn cos psi. For small tint angles, the distribution of backscattered electrons remains roughly symmetrical around the surface normal, and for larger angles, the surface tilt, the distribution of backscattered electron becomes asymmetrical with respect to the surface normal, developing a distinct lobe caused by a predominance of forward scattering. These effects cause the contrast in images formed with backscattered electrons to show a stronger dependence on surface topography and on the location and characteristics of the backscattered electron detector used. Also, the backscattered electrons' angular distribution is a factor that is affecting the BSE emission. It is defined relative to the normal to the surface, and it refers to the number of BSE escaping the surface at different angles phi relative to the normal to the surface. And the schematic diagram is giving the effect of angular distribution on BSE emission. Now, let us discuss about the electron beam and specimen interactions. And before learning that, let us discuss on the interaction cross section and the mean free paths. The probability of a scattering event could be determined by the interaction cross section sigma, or by the average distance an electron travels between two interactions, that is the mean free path lambda. Each scattering event might occur as elastic or inelastic interaction. Hence, the total interaction cross section sigma t is the sum of all elastic and inelastic terms, which can be estimated as sigma t is equal to sigma elastic plus sigma inelastic. Each type of possible interaction of electrons with a material of certain cross section depends on the number of electron atom scattering events, beam energy. By considering that a sample contains n number of atoms in a unit volume, the total scattering interaction cross section Qt is given as Qt is equal to n sigma, which is equal to n0 sigma t rho divided by A. Here n0 is the Avogadro's number, A is the atomic mass of the atom, and rho is the density. By introducing the sample thickness T, the interaction cross section results Qt times T is equal to n0 sigma t rho t divided by A, and this gives the likelihood of a scattering event. The term rho t is designated as mass thickness, and doubling the value of rho leads to the same Qt value as observed by doubling T. The mean free path is related to the scattering cross section by lambda MFV is equal to 1 divided by QT. For the probability of scattering in a specimen of thickness T, the probability P can be written as T divided by lambda, which is equal to QT times T. The angular distribution of electrons scattered by an atom during the electron specimen interaction is described by the differential cross section d sigma by d omega. The electrons are scattered by an angle theta and collected within a solid angle of omega as shown in the figure. The cross section sigma decreases with increasing in scattering angle theta, and the scattering into high angles is rather unlikely. The combined effect of the elastic and inelastic interaction are to limit the penetration of the beam into the solid, and the region of interaction between the solid and the beam is known as the interaction volume. Scattering in high angles or even backwards is unlikely in all materials, but the likelihood for them with increasing the atomic number. Furthermore, the beam broadening increases with Z, and the intensity of the direct beam is weakened by the deflection of electrons proceeding forward direction. Since the amount of deflected electrons and the weakening of the beam intensity depend strongly on the atomic number, different materials produces differences in the color contrast. In compact samples, most electrons of the incoming electron beam are observed in the specimen, resulting an interaction volume that has a pear-like shape. On their path through the sample, few electrons interact inelastically, losing a part of their energy. Although the probability of such events is quite small, but a lot of them appear if the sample is thick, that is, if the path of the electron through the sample is long. The smaller the energy of the electron, the higher the likelihood of its absorption on the sample becomes. However, some of the incoming electrons are even backscattered. The dependence of the shape of the interaction volume on the material and the voltage is schematically demonstrated in figure 13. The size of the interaction volume and the penetration depth of the electrons increase with increasing electron energy, that is the voltage, and decrease with atomic number of the material. For example, although secondary and auger electrons are produced throughout the interaction volume, they have very low energies and can only escape from a thin layer near the sample's surface. The volume of excitation, the size and shape of the interaction volume is limited by two factors. First is the energy loss through inelastic interactions. Second, the electron loss or backscattering through elastic interactions. Depth of penetration for an electron beam and the interaction volume of sample are function of the angle of incidence, magnitude of current, the accelerating voltage, and average atomic number of the sample. Electron penetration generally ranges from 1 to 5 micrometer, with the beam incidentating perpendicular to the sample. The depth of the electron penetration x is approximately x is equal to 0.1 E0 to the power 1.5 divided by rho, where E0 is equal to the accelerating voltage in kilo electron volt, and rho is the density, generally termed in terms of gram per centimeter cube. The width of the excited volume, which is Y, can be approximated as Y is equal to 0.077 E0 to the power 1.5 divided by rho. Now, the factors influencing the interaction volumes are: first, the influence of beam energy on the interaction volume. Here, as the beam energy is increased, the electron beam can penetrate to greater depths. There is no significant change in the shape of the interaction volume with beam energy. Second, the influence of atomic number of the solid in the interaction volume. In specimens of high atomic number, the electrons undergo more elastic scattering per unit distance, and the average scattering angle is greater. The electron trajectory in the high atomic number materials tend to deviate out of the initial direction of travel more quickly. The shape of the interaction volume is greatly affected by the atomic number of the specimen. And the third factor influencing the interaction volume is the tilt on the interaction volume. As the angle of tilt of the specimen surface increases, the interaction volume becomes smaller and asymmetric. So, students, let us summarize what we have learned in this module. First, we learned about the electrons from a source that interact with atoms in the specimen, yielding variety of photons and electrons via elastic and inelastic scattering processes. These are the signals that we use to make images and measure to characterize the composition of our specimens. The primary electron, after hitting an electron or a nucleus of the specimen, continues to a new trajectory known as scattering. The electron beam specimen interaction imparts various forms of energy phenomenon which can be provide some interesting information about the specimen, including topography and composition and many more. The secondary electrons, with low energy electrons about 10 to 50 electron volt, are generated from the collision between the incoming electrons and the loosely bound outer electrons, and can provide topographic information of the specimen. The factors like work function, atomic number, beam energy, beam current and surface tilt can affect the secondary emission of electrons. The backscattered electrons are high energy electrons produced during elastic scattering and can be affected by factors like beam energy, tilt, atomic number of the specimen. The interaction volume increases with increasing acceleration voltage and decreases with increasing atomic number. Thank you.